Thank you. Now, nuclear new builds, nuclear power stations, nuclear power plants are not themselves inherently geological. But geosciences nevertheless has a role in their construction, and primarily that role is in ensuring that those sites are safe, and in particular that they're safe from some of the very important external hazards that can create problems on those sites, and in particular seismicity is the obvious, perhaps the most obvious, but climate change also is another. But I'm going to primarily focus on the work that I've been doing with the Office of Nuclear Regulation Expert Panel for Seismic Hazard in relation to nuclear new builds. And it really feeds into this narrative about trust and about openness and transparency and working with the regulator, working on issues that are around legislation. And so it's a slightly different perspective, perhaps, to some of the other presentations that we've seen. Now, we've heard a lot already about the UK energy gap, and from a nuclear perspective, the current fleet of nuclear power stations, which currently produce about 15% of our current energy supply, is reaching the end of its life. The stations will become effectively obsolete in the next 10 to 15 years. And of course, in order to meet CO2 emission targets, the UK is also phasing out its conventional coal-powered generation. And as many people know, it's a truism really, we therefore face a significant energy gap over the next few decades, or potentially we do. And the view since the beginning of the new millennium has been that new nuclear could be viewed as being a part of the solution, because it is a relatively low carbon way to produce very large amounts of energy. And this is how it looked in 2009, and to be honest, I still find this a slightly mind-boggling diagram. You know, the plan was, this is from a DEC report produced in that year, for 10 to 12 new nuclear power stations by 2025. So that's not a very long Gantt chart. And there seemed to be many benefits. It gave the UK an improved energy security for the medium-term future. It was going to produce lots of jobs for very skilled people, for engineers, for scientists. And it was going to represent a very significant boost to the manufacturing and services base in the UK. In fact, it was going to be one of the largest infrastructure projects. And we've heard many times recently about the importance of major infrastructure projects in terms of the well-being of the UK economy. Now, we have to remember, of course, that since 2007, the Scottish Parliament, however, has opted out of this and has a policy of no nuclear new builds in Scotland. But of course, this very optimistic view that was expressed in that DEC report back in 2009 was before this happened. This is Fukushima. And Fukushima and the consequences of Fukushima resonated very strongly in the nuclear industry right across the world and led to effectively a sort of cessation of nuclear new build activities for well over a year. And so by the time we get to 2016, the plans in the UK had downsized somewhat, and the sort of sites that were being talked about for new nuclear plants at that point were Bradwell, Hinkley Point, Moorside, Sizewell and Wolfer. But that's still 5, that's still not bad. It's only half as big as what we had before. But of course, as we know, relatively recently, this has also run into significant difficulties. And I would comment, and it's merely my personal opinion, that perhaps what we're seeing here is the problem, and I suspect this is something we may discuss this afternoon, that really, for something as big as nuclear, is it really sensible to let the market decide? Or is this something that really, if you're going to go this way, you need serious state investment? But we've seen that Moorside has been abandoned. Wolfer is, shall we say, in significant difficulty, and there are now calls for an independent review of the UK's energy policy, the basic argument being we're in a bit of a mess. Now, the reasons behind these problems are not inherently geological. And of course, Hinkley Point C, is being built. And Bradwell B and Sizewell C are still in development at this time. So my raison d'etre and that of the Office of Nuclear Regulation hasn't completely gone away. Now, as I've already indicated to you, the geosciences are really particularly important from the point of view of nuclear new builds in terms of considering the suitability of a site and its long-term safety. And this what I really want to try and outline is what are some of the challenges that you face here, and what are some of the important scientific advances that are then feeding into this safety assessment. But it also feeds into the issues around legislation, regulation, and assessment. And that is the job of the Office of Nuclear Regulation. Here's one of these wonderful maps that government organisations love to produce, showing how they all interact with one another. This is the ONR here, the Office of Nuclear Regulation, and how it interacts with the various other parts of the UK government apparatus and the Health and Safety Executive, and of course the new licensees. And here are its roles, okay? It regulates the nuclear new build process from concept design to operation. It regulates the process of the decommissioning of those facilities. It inspects nuclear license sites in order to make sure that they're compliant with their license conditions, and it can take enforcement action. It is an organisation that has legal teeth when licensees fail to follow the rules and meet the required safety and security standards that are enshrined in law. So this is an important organisation. Now, from the point of view of new builds, the obtaining of a nuclear licence is really very important. And the ONR have published what the regulatory expectations and the process are in a recent document, which came out, I think, in 2011. And you see here that in order to get a licence, there are a whole series of key areas that you have to cover. But one of the most important is really focuses around this design and safety case. That before a licence can be granted, the ONR needs to be satisfied that the choice of site that has been made by the applicant is suitable. That's to say that the hazards are understood and that there's a suitable schedule of safety submissions put in that basically gives confidence that the hazard and the risk is reduced as far as possible. Now, from a geological perspective, of course, hazard. Well, what is a hazard? Hazard is an event or a situation which has potential to cause an accident. And accidents in nuclear power stations, by their very nature, are a bad thing, as we know. And geology is particularly relevant from the point of view of external hazards. That's the hazard over which a licensee has no direct control. And these generally originate off-site. And they fall into two groups, natural hazards and man-made hazards. And it's the natural hazards where the geological ones are. Seismicity, extreme weather, flooding. Because of my experience, I'm going to talk primarily about seismicity. And I'm going to do that partly because seismicity is also one of the more difficult external hazards that the industry has to deal with. But here's some of the documentation related to the legislation and the process. This is a very, very busy diagram, for which I apologise, but I just want to mention it. The whole process of developing a safety case is covered under a series of what are called technical assessment guides, or TAG 13. TAG documents, TAG. And TAG 13 is the set of documents that deals with external hazards. And it basically has a number of different levels. It has a head document, then a series of annexes which relate to each of those external hazards, and then below those we have some external panel papers, which are, if you like, an exposition, dealing in a more informal way of some of the issues around those hazards. And it's very structured. But I'm going to talk about seismic hazard, okay, because I sit on the expert panel for seismic hazard and climate change. What it is there, or its stated aim is to provide credible, independent evidence to support ONR's regulatory role and its actions in dealing with the licensees. And we help with their decision making, and we are involved directly in the assessment of the safety cases. Now, as I've said, seismic hazard, it's one of the most geological external hazards, obviously, and it's one of the most problematic for the nuclear industry because it's a major common cause fault initiator. What that means is basically it causes a whole series of breakdowns in a site and will affect all parts of the site simultaneously by its very nature. It can create secondary problems like floods or fires. It's extremely difficult to isolate the plant from seismicity. And it is, of course, earthquakes are by their very nature unpredictable. Slightly strange that I should have to remind, but that's just to remind you that, of course, earthquakes are produced by sudden ruptures along a geological fault at depth. Okay, that releases elastic strain energy, which then, a proportion of which radiates away from that source in the form of seismic waves. The fault may also, which produces shaking. The fault may also, of course, break up to the surface and produce a surface rupture. And that kind of fault is referred to in nuclear terms as a capable fault. And it actually breaks the surface and can also cause severe disruption to a facility that would be sitting on top of it. But of course, not all faults break to the surface. They may be blind. Now, in terms of earthquake processes and hazards, there are quite a number of these, okay? So we have the faulting process itself. The faulting process itself can produce surface ruptures, like this, and can produce tsunamis, as we saw at Fukushima. The seismic energy, of course, produces strong ground motion, shaking. That shaking itself can cause damage to man-made facilities, but you can also get a series of secondary effects, landslides and liquefaction, which were seen very beautifully displayed, well, not beautifully from the perspective of the people who live there, but very, very geologically spectacular examples were associated with the Christchurch earthquake. So these represent the sort of processes and hazards that you're trying to deal with and mitigate against. Now, in terms of how one mitigates against those various hazards, in the UK, a site that potentially has a surface rupture, that is considered to be an exclusionary issue. And so you have to ensure that you can basically remove that as a possibility for the site on which you're building. In the case of tsunamis, what you do is you basically try to design, come up with a design basis that will allow you to deal with that. And in the UK, we're talking about coastal flooding. So you maybe build seawalls, you maybe build your site on a platform that's elevated. In terms of landslides and liquefaction, basically you identify the possibility of that hazard and try to eliminate it using geoengineering measures, or you don't build in that particular place. And then for the shaking issues and the things around that, you try to define a design basis, basically a facility that will be able to withstand that shaking. Okay, so that's the sort of background, the process, and a new nuclear build. But what about the UK? Well, as we've already heard from a number of presentations, the UK has a very, given it's such a small place, a very diverse and long geological history. Geology, of course, powered the Industrial Revolution. It kick-started a lot of what happens in oil and gas. And in many respects, and that's partly why this building is here, it was the birthplace of modern geology. But it would be wrong to say that we should therefore think that we know everything that we need to know from the point of view of nuclear new builds. And it has been suggested to me, surely we don't need to know any more, do we? Well, yes, we do. We also know that Britain has a long legacy of geological structures, the sort of geological structures that potentially could produce earthquakes. We know that British crust is full of faults, continental shelf too. Some of them are as old as 2.5 billion years old, and some of them have been reactivated multiple times throughout geological history. And it reflects a very long and turbulent geological past in this country. But of course, in terms of the current tectonic regime, since the opening of the North Atlantic, Britain has sat on a relatively quiet, passive margin. There's relatively little tectonic activity. And what we know about the tectonics is that basically Britain is in a current northwest-southeast compressional stress regime due to ridge push from the North Atlantic and the sort of residual effects of the alpine orogeny in southern Europe. That regime is modified somewhat due to glacial isostatic adjustment, the loading and unloading of the Fennoscandian ice sheets. But, you know, it's a typical intraplate region. So what about the seismicity? Well, the seismicity of the UK is actually a bit enigmatic in some ways. Most of the earthquakes are relatively small and cause little damage. Most of them are strike-slip, and this seems to be consistent with the northwest-southeast compression. So it does suggest that the sort of overall tectonic control of our earthquakes is from the far-field tectonic stresses. But the problem is that it's a very incomplete record. Here are some notable earthquakes. The largest earthquake in the UK occurred that we know about was in 1931, occurred out in the central North Sea. There may have been bigger events that occurred out on the continental shelf, perhaps as high as magnitude 7, back in the 1500s. But our record maybe isn't long enough to extract reliable information concerning earthquakes, and that's a bit of a problem. We don't have any unequivocal examples of active faults at the surface in the last 10,000 years in the British Isles. Thus, the seismicity that we see here must be occurring on faults that don't reach the surface, blind faults. And it's actually very difficult to relate even these earthquakes to known geological faults at depth. And that's, again, it's very typical of intraplate seismicity. But a very important thing to remember here, and a thing that is a sort of bit of a mantra in our safety case assessment, is that absence of evidence is not evidence of absence. We should not assume that, surface rupturing faults or big earthquakes are going to be a problem. They're not going to be a problem in the UK. We don't know that. We have to present all the evidence as much as we possibly can. So a safety claim or a safety case is all about claims, argument, and evidence. And according to the ONR, a safety case should show that a nuclear power plant is safe and that hazards are adequately defined and that risks that arise from plant failures are as low as reasonably possible, a LARP as it's called in the technical jargon. It has to present objective evidence and, very importantly, at every stage must involve independent peer review, which is documented with all the challenges and the resolutions of those challenges being shown in the open. Now, in terms of what happens in the UK, as I've mentioned, capable faulting surface rupturing is regarded as exclusionary and therefore important, and that's covered in most cases by a capable faulting study. And then the shaking part is covered by the PSHA, which is a probabilistic seismic hazard assessment, which is a bit less geological, but is ultimately underpinned by the geology because that's where the shaking is coming from, a geological fault. Now, a number of these studies are going on in UK Newbuild sites, and the most advanced are at Hinkley Point C and Wolf and Newhead. And there are also studies ongoing at Sizewell and Bradwell. And those studies, the findings of those studies and some of the difficulties that those studies have faced have actually informed the contents of all of those TAG documents and the annexes and the expert panel papers. So there's an interactive feedback process that's been going on. And again, this is all part of this broader theme of trying to be transparent and trying to make it as accessible to all as possible. And we've been very pleased to see that some of the work derived from the Hinkley C safety cases has already been published by EDF in the scientific literature. We view that as being a very good thing. Now, just wanted to say a bit about capable faulting because it's kind of my thing on the panel. There's no unambiguous evidence of surface rupture in the UK, although at least one person in the audience, Phil, wherever you are, will recognise this, the Kinloch Horn fault in northern Scotland, about which there has been a discussion in the past as to whether it is a recently active fault. But it is nevertheless very important to demonstrate that this hazard for surface rupture is very low if it's going to be screened out for a site. And now, in terms of the sort of methodology that is now recommended, basically what the licensee has to do is to come up with a comprehensive and up-to-date description of the surface and subsurface geology for their site. It starts with a desk-based compilation of the regional geological information and existing geological and geophysical data, of which there's a very large amount, which is where the PSHA analysis also starts. But we also expect new data to be collected. Okay, that might include new surface geological mapping and interpretation. It might include structural and lab-based microstructural characterization of the faults, the fractures, and the exposed rock formations. It includes a whole range of subsurface investigations, geophysical surveys, borehole analysis, and logging of the cores. It includes an in situ stress study, perhaps through the borehole, and might also involve a slip tendency analysis, where you look at essentially how prone specific geological fault orientations are relative to the modern stress field for slip. And it could also include a study of the relationships that might exist between known geological faults at depth and earthquakes. All of this is then pulled together to build an integrated three-dimensional model of the underlying geology and faults in the crust below a site. And for large faults that have repeated movement histories or faults that are favourably oriented for slip or faults that are rich in weak materials like phyllosilicates, for example, particularly smectites, it may be necessary to underdo still further studies, radiometric age dating, for example, or testing of frictional strength. And these are all things that have happened in safety cases that are developing right now. Now, the sort of parallel part of this stream, the PSHA, this is a traditional way now that seismic hazard is addressed in areas of low seismicity, using a probabilistic approach. Basically, what it does is it combines geological and seismological data to calculate the probability that a certain level of ground motion will be exceeded over a given period of time. And in regional, this is a regional PSHA or approach in this particular example here. What it shows is that there are two particular seismic hotspots, if you like, in the British Isles, in Snowdonia and southern Wales. And those lie quite close to some significant nuclear facilities. The various components of a PHSA are shown here, and what these are basically all about, they're about asking, well, where will future earthquakes occur? And this usually involves coming up with some sort of seismic zonation model. It's a question of then, how often will the future earthquakes occur of different magnitudes, and what's the likely largest event that you're going to see? Trying to then predict what the ground motion levels are going to be for your particular site, and then come up with some sort of seismic hazard curve, a probability of exceedance, a best estimate, if you like, of the hazard, and then engineer to deal with that. Generally speaking, what a PSHA involves are these various things. Involves looking at the old earthquake catalogue and understanding and discussing its completeness, looking at developing a number of plausible earthquake zonation models, coming up with ground motion prediction equations and site response characterization, and dealing with this issue of trying to quantify and discuss epistemic uncertainties. Those are uncertainties which arise due to our lack of knowledge requiring earthquake surface processes and seismic wave propagation, both in general, but also for the specific site. And then finally, it involves doing some PSHA calculations to come up with those final hazard curves. Now, there's actually another narrative that's become apparent to us as we've been reviewing safety cases, and that was we discovered in the early days that a lot of the time the capable faulting study and the PSHA were done in isolation from one another. And when you looked at the evidence that was being presented in one, it wasn't consistent with the evidence being presented in the other. And that's plainly ridiculous. Because, of course, ultimately, surface rupture and ground shaking are linked. They're linked to geological faults. And so it's very important that the analyses that are carried out and the narratives here between those two studies link together into a single overarching whole. They must be consistent with one another. Now, I want to return finally in my penultimate slide, no, it's not my penultimate, it's my penultimate slide, to this issue of trust. And I'm not going to say a great deal about this, but it is very important because one of the lessons that's been learned in the USA was that it is very important to make the process as open and as transparent as possible, but also that it's robust. And the sort of world standard now for nuclear new build safety cases is the SHAC approach, which stands, SHAC is a shortening of Senior Seismic Hazard Assessment Committee, and they have 5 points of light that they say need to be considered when you're looking at a PSHA and a capable faulting study. And I'm not going to go through them, but what they're all about, two main things. They're about, first of all, is the study complete and covers all the possible range of possibilities? But most importantly, was it done in a transparent way? And was it done rigorously? And a specific message that comes out of these 5 points is the idea that you have to have consulted a very wide range of independent experts during the whole process, right from the beginning through to the very end. And those experts are involved, therefore, in the creation of the safety case and in its assessment. But what about the geology? Because after all, we're here to talk about geological things. Well, I think there's a geological revolution going on that's associated with the assessment of nuclear new builds as well. I've seen the use of some new radiometric dating techniques on some of the fault rocks, fracture fills, to try and date when the faults last moved. This includes things like potassium-argon dating of illite size fractions in fault gouge. It includes things like uranium-lead dating of calcite, and rhenium-osmium of base metal sulfides. They've all been used. These are cutting-edge pieces of work and can be published in the scientific literature, and I very much hope that they will be. There's now an appreciation that fault microstructures, deformation mechanisms, and how those then impact upon the frictional properties and mechanical strength of fault rocks. That too is becoming much more aware of, or we're much more aware of that now in these studies than we have been in the past. But do you know what? I think it's actually, there's a revolution going on that I see parallels with the oil and gas industry, and that is that the licensees are now developing these multifaceted GIS models that incorporate all the information that they've collected into a single georeference database, a single viewing platform, so that what you have is, therefore, these models allow you to include your geological information, your geophysical information, magnetics or gravity, your boreholes, your seismic sections, whatever, and produce a fully three-dimensional model of the underlying geology on the sites. And to me, this is a geologically led revolution coming from many of the approaches that have been used in the oil and gas sector, and it's actually passing into the civil engineering sector. And I think that this is a step change in the way that the civil engineering is done. They're finally taking geology seriously. And on that note, I shall end. Thank you.
Great, thank you. Okay, do you have questions for the speaker?
Given what you said about transparency, do you think the ONR should take a more active role in the communication of nuclear risk? Because take Fukushima, for example. That had, like you said, a massive effect on the sector. But the reason that happened is because they didn't expect to have a 15-metre wave tsunami and knock out the backup generators. Whereas the general public consensus would not be that's the reason it happened. So do you think organisations like the ONR should be taking more of an active public role in it?
Yes, I do. And I mean, that's a discussion that we regularly have at the panel meetings. And actually, I mean, at the level of the I have to be a little bit careful what I say here, but I think it's true to say that many of the nuclear inspectors are of the view that, yes, the ONR should be doing that. So I agree with you. I think that it is important because, and it comes back to this thing of being seen to be objective and independent of the nuclear industry, which it is. But I think that if there was a little bit more on the terms of public communication of science and what the issues are around this, that really would help. So yes, I think they should.
Not really to do with the geology, but a general comment on the list of potential hazards that you showed. I thought a startling omission was terrorism or other things related to potential civil unrest, even warfare. With such a critical issue as nuclear power stations.
To be clear, there is a whole process. There is a whole process within the TAG process that looks at that, obviously, because that is a very important. I specifically said that I wasn't going to talk about man-made hazards, but there is a process. It is equally rigorous. I mean, I was dumbfounded to find out that all nuclear power stations are actually engineered to withstand aircraft collision, which to me was news to me. I was quite surprised by that. So that be assured that there is a very rigorous process in place. It's just that they're not geological. So as a geoscientist, I'm not involved in those. But it's a very good point. And if I didn't make it clear, it certainly is the case.
Time for one more question.
John Midgley, BGS. How do you handle the known unknowns? Is it as simple as a weighting number in the probabilistic model, or do you leave it till the end and then just discuss the general unknowns?
No, there is a process for doing that using logic trees, where you then assign different branches are assigned a probability, and there is a well-known process to go through that addresses that. So it's done using a logic tree approach. But it's important to say that you need to develop more than one possible model, okay? And then this issue of consulting a wide range of experts and getting expert opinion also feeds into giving confidence that the weightings that are given for those different branches are appropriate. And that's been one of the biggest areas of discussion that we've had with some of the current nuclear new builds, as some people in the audience know. So